Ever wondered how to prove something true for every natural number? Today we are going to learn one of the most powerful proof techniques in mathematics, mathematical induction. Mathematical induction is a technique used to prove that a given statement is true for all natural numbers like 1, 2, 3, 4, and so on till infinity. Instead of checking every rule one by one, we use a smart logical shortcut. The idea of induction is very simple. If the first step is correct and every step automatically makes the next step correct, then the entire chain becomes true. Before moving ahead, let me quickly explain one important word, domino. A domino is a small rectangular standing tile used in a game. When one domino falls, it pushes the next one. Then that second pushes the third. And in this way, the whole line falls automatically. Mathematical induction works exactly like dominoes. If the first domino falls and every falling domino makes the next one fall, then the entire line will fall. This exact same logic is used in induction for proving infinite statements. Mathematical induction always works in two compulsory steps. The first is called the base case, the second is called the inductive step. If both steps are correct, the proof is 100% confirmed. In the base case, we simply check whether the given statement is true for the first value. Usually n is equal to 1. This is like checking whether the very first domino falls or not. In the inductive step, we assume the statement is true for some number k. Then using this assumption, we prove that it must also be true for k plus 1. This is like proving that every domino will push the next. Final logic is if the first step is true and every step guarantees the next one, then by logic, the statement becomes true for all natural numbers. Now, let's apply all this theory to our first simple and famous example using mathematical induction. Our goal is to prove that the sum of first n natural numbers is equal to n into n plus 1 divided by 2 for all natural numbers. First, we check the base case. That means we put n is equal to 1 and verify both sides. When n is equal to 1, the left side becomes 1 and the right side becomes 1 into 2 divided by 2, which is also 1. So the base case is verified successfully. Now, next inductive step. We assume the given statement is true for some fixed natural number k. This assumption is called the induction hypothesis. Our next goal is to prove that the statement must also be true for k plus 1. We start from the left hand side of k plus 1. We separate the last term and use our assumption for the remaining part. Now we replace the sum till k using our induction assumption. We get k plus 1 into k plus 2 divided by 2. Now RHS we put n is equal to k plus 1. For k plus 1th term we get k plus 1 into k plus 2 divided by 2. This is equal to LHS. Hence, inductive step also verified. Hence, the statement is true for all natural numbers.
Now, let us take a slightly harder and very important inequality proof using mathematical induction. For base case n is equal to 1, both sides becomes 2. So the base case is verified. Now we assume that the inequality is true for some natural number k. So 2 to the power k is greater than or equal to k plus 1. Now our aim is to prove the inequality for k plus 1. We start by rewriting the left hand side. Using equation 1, we replace 2 to the power k into 2 is greater than or equal to k plus 1 into 2. So comparing LHS RHS, we get 2k plus 2 is greater than or equal to k plus 2. Always for all k is greater than or equal to 0. So the inequality holds true for all natural numbers greater than 1. By mathematical induction, also this proof teaches us a powerful concept. Exponential functions grow much faster than linear functions. Next, in strong induction, instead of assuming only one previous case, we assume all previous cases are true. Strong induction example. This is a famous result known as the fundamental theorem of arithmetic proved using strong induction. Since 2 itself is prime, the base case is true. Then inductive step. We assume that all numbers from 2 up to k can be written as a product of primes. Now, if k plus 1 is prime, the result is immediately true. And if it is composite, it can be written as a product of two smaller numbers, which are already expressible as products of primes by assumption. Inductive hypothesis. Hence, by strong induction, the theorem is proved. These are the four most common mistakes students make while solving mathematical induction problems. First is forgetting base case. Second, wrong k plus 1 substitution. Third, assuming what you must prove. And fourth, algebra mistakes. Now, here is your first practice question from this chapter. Using mathematical induction, prove that 3 to the power k is greater than n cube for all natural numbers greater than or equal to 4. Pause the video here, try it yourself honestly, and then continue with the solution. Now, solution. Let's start with the base case. We substitute n is equal to 4. Left hand side becomes 3 to the power 4, which is 81, and right hand side becomes 4 to the power 3, which is 64. Since 81 is greater than 64, the base case is verified. Next, inductive step. Now assume that the inequality is true for n is equal to k. That is 3 to the power k is greater than k cube. We now prove it for k plus 1. 3 to the power k plus 1 can be written as 3 into 3 to the power k. Using our assumption, this becomes greater than 3 into k cube. Now for all k is greater than or equal to 4, 3k cube is always greater than or equal to k plus 1 cube. Hence the inequality is true for k plus 1. Therefore by mathematical induction, 3 to the power n is greater than n cube for all n greater than or equal to 4. Next question. Now we prove a very nice factorial identity. Sum of r into factorial r from 1 to n equals n plus 1 factorial minus 1. Try to see pattern first, then we will prove it. So base case n is equal to 1, LHS is equal to 1, RHS is equal to factorial 2 minus 1, which is equal to 1. So base case is true. Next, induction hypothesis. Assume the statement holds for some k. Now prove for k plus 1. Using the hypothesis, the sum up to k is k plus 1 factorial minus 1. So sum up to k plus 1 is k plus 2 into k plus 1 factorial minus 1, which is equal to k plus 2 factorial minus 1, which is the right RHS with n is equal to k plus 1. Thus by induction, the identity is true for every natural number n. So, in this chapter, we fully mastered mathematical induction from basics to advanced level. If you truly understood the logic of induction, you have unlocked the power to prove infinite results with finite steps. If you want to learn mathematics with full logic and real understanding, not just formulas, then subscribe to my channel right now. Many powerful conceptual videos are coming next. Let's grow together in this journey of smart learning.